to kind of keep talking about. Effectively, when we're doing these the Xenon stuff and Samarium stuff, we're really doing production destruction equations, and we're doing applications of production destruction equations for oops, for specific nuclides. So that's what we're going to keep talking about today. Before we got into the content, I just wanted to remind us about what the end of the semester looks like. Today is lecture 16. The rest of this week, I'm going to be out on travel, so we won't have our regular Tuesday help session. And then Wednesday, we will have class, but it won't be like it'll be asynchronous. I'll post a video and I'll post a quiz on Canvas that will be based on what we talked about today and also what's in that video. You would just want to watch that video and then respond to those questions. That quiz on Canvas will have a due date that's the end of the day tomorrow or the end of the day on Wednesday. So just make sure that you watch that video and answer those questions by the end of the day on Wednesday. Um, Monday is our last day of class. That's where we will do a combination of final exam review and help session review about the project. Um, and so I will talk like kind of briefly, like maybe for 20 or 30 minutes or so about the final exam and things to be aware of. Um, but I've already posted the final review. And so my hope is that by Monday the 3rd, you'll have looked at that review. You'll have also been working on the project such that most of that class time is going to be student focused, dedicated to answering any questions that you have, last minute questions about the project or questions about the final. Um, the project will be due on the end of the day on the 3rd. So making sure that you are working on that would be a good thing. I know that some people are already pretty far through that. So if you are not making good progress, you're going to want to start sooner rather than later. I can almost guarantee that you're going to end up with questions about that. So starting sooner means that you can get your questions answered sooner. Even though I'm not going to be here for the rest of this week, I will still be available over email. So I would encourage you to send me questions as they arise, and I'll respond to them like within a day. Um, we will have our normal Tuesday help session the following Tuesday on the 4th. And so the project will already have been hopefully submitted by then. So that 4th will just be our last help session where we'll exclusively focus on the final. And then that final will be here in class on Wednesday the 5th from 1 to 3 p.m. And so make sure that you come to that come to class on the 3rd with questions. Make sure that you come to that help session with questions, and make sure that if you have questions before then, that you reach out and let me know. So the final exam, I'd already talked about when it is. It's going to be very similar in terms of what the previous exams have looked like. Same format, same kind of breakdown of the questions. You'll also have a couple bonus questions on there, and it will be cumulative. So it'll cover everything from exam 1, exam 2, and then the stuff that we've been talking about in chapter 8, the production destruction equations, Xenon and Samarium buildup, and then you'll have a couple concept questions from what we talk about in the next lecture on reactor analysis. So if you go on the Google Drive, there's already a review posted there, and the formula sheet is already posted there as well. You want to be familiar with those things. They will tell you pretty specifically about what to expect for the exam, and you'll have all of those equations that you can be using to practice. You want to be familiar with those equation sheets. Some answers to the exam questions will almost just be straight from that formula sheet. So making sure that you know what formulas are there, how they apply, when to use them is really important. Because like even if you don't know exactly how to do a problem, if you know more or less like, okay, this problem is based on like one group diffusion theory, or this problem is based off of like the matrix form of the point kinetics equations, or this question's asking me about the coefficient of reactivity. If you know where those things are in the exam formula sheet, then you can at least write that thing down and like get some partial credit, even if you don't know like all of the steps that you would have afterwards. And I have your exam twos graded. I'll pass those back at the end of class. Um, Friendly reminder about course evaluations. These are technically open now. You can go to this website, tamu.afis.net, to complete them. I would really appreciate your feedback on the course. I I signed up to teach the class because I like teaching and I want to be a professor someday. And so this is a hard class. I've tried my best to teach it in a way that I think is fair and a way that I would have liked to have had the class taught when I took it as an undergrad. So if you've liked the class or even if you don't like the class, I would still appreciate your feedback so that I can know things that I could possibly improve on if I end up teaching it again. So yeah, if y'all could take some time out of your day, they close on the 4th of August. But if you could take some time to complete those, I would really appreciate it. So gonna kind of review a couple of the topics that we covered last class, which will then lead us into like where we couldn't finish from the last class. So one of the concepts that we had been talking about is fuel burnup. That is the process by which, as your fuel runs in a reactor, your concentrations of your fissile nuclides decreases, and we can say that those nuclides get consumed or they get burned up, or they get depleted. And so burnup is a measure of how much energy we get out of the fuel that's in our reactor. You can talk about it in terms of like megawatt days per mass of heavy metal in the reactor. You can also talk about it in terms of the percentages of atoms that have been fissioned. If we think about it from that first definition, then this is the formula that you can use to compute burnup. It's your power in megawatts times the time that the reactor was operating, time at rated power in days, and then divided by how much mass of initially loaded heavy metal that you had. That fission power is related to the power density, um, which would be like the volume integral of the power density would give you the power. And therefore, the burnup depends on the flux. And the flux is position dependent, which means that your burnup is also position dependent. Different places in your reactor will actually burn up fuel faster or slower, depending on where the flux is in your reactor. Um, and burnup is like if you hear people talking about reactor designs, um, burnup is something that you'll hear brought up. We in the US and in other places are trying to get better use of our fuel. Like uranium is like a finite natural resource. And so being able to go to higher burnup means that you're getting more use out of your fuel, which is good for like in terms of conservation. It's also just good in terms of the economics of our reactors because it means that they can run for longer without having to be turned off. And reactors usually run for like 12 to 18 months, and then turning them off is like a multi-week process of like refueling them, doing maintenance and stuff like that. So if we can run them for longer, it's more economical, and it's also how we can get more energy out of the reactors that we have. Um, in the burnup calculation, if you write the burnup, if you write the power in terms of the flux, then you'll end up with a multiple of the flux and the time interval. And the flux times the time interval is something that we can define called the fluence. Um, if the flux is time dependent, then it's the time integrated neutron flux. But if the flux can be approximated as being constant with time, then the fluence is just the flux times the time interval. And the fluence is kind of like your flux, except it doesn't have the time units in the bottom. So it's basically telling you about the path length made of neutrons per unit volume over some time period. And it's very much related to, well, I mean, it's in the burnup calculation, so it's related to burnup. You can also use the fluence as kind of like a radiation materials topic, in that it will directly relate to how much your materials in your reactor get deformed or like how much they get damaged by the high radiation levels in our reactors. You can relate it to something called the number of displacements per atom, which is like a material science thing that tells you like if you have like a steel pressure vessel, how many displacements the atoms in that pressure vessel have undergone per atom. And that's a consequence of the flux acting on those materials and causing them to change. So we've been talking about production destruction equations. We've been talking about the buildup of fission products. We have talked about how fission products, their buildup is important in terms of analyzing time dependence of reactors because they influence our reactor operation because a lot of these fission products can be very highly absorbing. If they have high absorption cross sections, then that means that they impact our K effective, and that means that they impact our reactor operation. Um, So we had talked before about how like you get basically everything on the periodic table coming out of your fission reactions, and you can group all of those fission products together as a pseudo fission product, which kind of like takes all of your fission products and considers them as one thing with some like average properties of the absorption of those products. But some of our individual fission products have such outsized cross sections that it's probably better that we explicitly model them by themselves versus lumping them with our as pseudo fission products. And so those are the ones that have like the largest absorption cross sections are the ones that we need to explicitly model. And for us, the main two that we're concerned with is Samarium 149 and Xenon 135. The buildup of these things happens on like the on the order of like hours of reactor operation, and the buildup of these things is really important in terms of from the moment that you start a reactor to the moment that you shut it down, and then the moment that you try to like start it back up. The buildup and depletion of these fission products can actually put your reactor in a configuration that would be unsafe if you were unaware of the concentrations of these fission products. So that's what we're going to talk about more today is how to predict what the concentrations of samarium and xenon do in our reactor to understand how that impacts reactor operation. The first one that we talked about was samarium 149. You get samarium not as a direct fission product, but from the decay of fission products. So if you have fission, some fraction of those fissions will produce something called neodymium 149. Neodymium is very radioactive. It beta decays into promethium 149. Promethium is also radioactive, but it has a much longer half-life. And eventually, promethium decays into that samarium 149. Samarium has a capture cross section of about 4 times 10 to the 4 barns. So it's very good at capturing, especially thermal neutrons. And samarium 149 is not radioactive. So once you make samarium in your reactor, the only way you can get rid of it is by it capturing a neutron and becoming samarium 150. Um, what we talked about last time is that because the half-life of neodymium is so short, we can kind of like ignore the neodymium part of this chain, and we can just assume that the fission directly produces the promethium with some yield that corresponds to the fission yield of neodymium. And recall that the fission yield, this YI to 149 neodymium for a group G, is basically saying if I have a neutron of in group G that causes a fission, what fraction of those fissions of that type I nuclide produces neodymium 149? And so fission directly produces promethium, which decays into samarium, and then samarium absorbs a neutron to become samarium 149 absorbs a neutron to become samarium 150. And we can also assume that, like, technically, sometimes when promethium decays, it will decay. It has a like a multi-decay pathway, but we can, for simplicity, assume that 100% of those decays result in the production of samarium 149. So we're assuming that that yield of decays from 149 promethium always produce samarium 149. So in our simplified product chain, we're saying that the promethium comes directly from fission, the promethium always decays into samarium, and then samarium has to capture a neutron. 149 captures a neutron to become samarium 150. So the nuclides that we would be keeping track of are the promethium and the samarium. If you look at promethium here, it gets produced from fission. So it has the rate of change of the promethium is a gain minus a loss. The gain is due to fission yield, and then the loss is due to it decaying. And if you fill in the terms for the fission production density and the decay loss density for promethium, those are what those terms would look like. And then with samarium, it is gained because of the decay of promethium, and it's lost because of absorbing neutrons. So its gain rate for samarium looks like a decay gain density from the promethium decaying into samarium, and then the loss rate is based on the absorption rate density for the samarium itself. So the decay gain term looks like the decay density of promethium. The loss term looks like the absorption rate density for the samarium. And so these are just first order ordinary differential equations. If we knew the initial conditions or the initial concentrations of my promethium and my samarium, then we could solve these differential equations to predict how those concentrations of these isotopes evolve with time. So this would be the initial value problem. If we assume that time 0 is at like the beginning of the fuel before we've ever turned the reactor on, then there will be none of these isotopes at time 0 because no fissions have happened that can build them up. And so if these are our initial conditions and these are the differential equations that govern the process, then we can solve these sets of equations to get these solutions. So this is telling me about the concentration of promethium as a function of time, and this is telling me about the concentration of samarium as a function of time. And both of these would have to be found using integrating factors. These are not separable equations, so it's a little bit more complicated in terms of finding what these solutions are. In an exam, I wouldn't ask you to solve something using an integrating factor, but I could possibly give you these solutions and then tell you to do stuff with them. So yeah, just keep that in mind. Um, we had talked about equilibrium concentrations of these nuclei, meaning that we're assuming we turn the reactor on and then we let that reactor operate for like a long period of time. And we would be wanting to know, once this reactor has been operating for like 100 hours or 200 hours, what concentration of these nuclides have been built up. Because if we build up an equilibrium concentration of like samarium 149, then we have a lot of this very absorbing isotope that's now in our reactor. And if we don't account for that, if our reactor was initially critical with K equals 1, and then we built up a bunch of this highly absorbing material, K is no longer going to be 1. K is going to go subcritical because we've added so much absorbing material to our reactor. So we need to know what concentration of these things builds up so that we can know how do we adjust our reactor properties such that we remain critical as this thing gets born. The way we can find the equilibrium concentrations is by just taking these solutions and then taking the limit as t goes to infinity. And so this is what we did last time. We took the limit as t goes to infinity of these terms and of these equations, and we noticed that all of the only place we see the variable t, little t, is in these exponentials, and all of these exponentials are negative. So if you let t get very, very large, all of these negative exponentials just go to 0. And therefore, for promethium, the equilibrium concentration is just this constant up front. And then for samarium, its equilibrium concentration is just this constant up front, because these exponentials go to 0, so you just have 1 times this guy for promethium, and then these two exponentials go to 0, so this entire term for samarium becomes 0. This exponential goes to 0, so then you just have 1 times this guy for the equilibrium concentration of samarium. And if you notice in these equilibrium concentrations, the promethium concentration depends on the flux, whereas the concentration of samarium doesn't depend on the flux. So if you operate your reactor at higher fluxes, you're going to produce more promethium. It's directly proportionate to the flux. If I ran the reactor at double the flux, I would get double the amount of promethium in equilibrium. So we're imagining now that the reactor's been running for a long period of time, and then we've got to shut the reactor down. We've got to scram it. And so we're going to say that at some time t0, we've scrammed the reactor. That means that we've like dropped all of the control rods into the reactor. And what we can say is that if the reactor, we can assume it was operating at a constant flux before we scrammed it. So at time t0, our flux was this constant value of the flux, but then after we've scrammed it, the flux is now 0. There's no more flux in the reactor. And so these if we want to say how does the concentration of these nuclides evolve after the scram, we have to resolve those differential equations, but we're solving them with the flux term being 0 in our equations. So if you were to go back and take these equations, sorry, if you were to take these equations, but you're setting the flux equal to 0, then this term goes away and this term goes away. So if the flux is 0, it simplifies our differential equations. It makes them a little bit easier to solve. Like this promethium one is just going to look like a decaying exponential, and the samarium one is just going to look like an exponential like production term. And the initial concentrations of our nuclei would be the amount that there was at time t0 when these things were in equilibrium. So the initial concentration for promethium when I'm shutting it down from running at full power for a long period of time, this equilibrium amount of promethium becomes like my new initial condition. And same thing with my samarium. That equilibrium amount of samarium would become my initial concentration of samarium from the moment that I'm shutting the reactor down and then letting time move forward from there. So these are what those equations would look like in terms of how these nuclei concentrations evolve after the shutdown. And if we take a look at these equations, it kind of makes sense that the promethium is just a decaying exponential, that this thing is just going to keep going away because its production was due to the flux, but the flux is now gone. So it has no gain term. It only has a loss term due to its self-decaying. Um, Whereas with samarium, it gets continued to produce because the promethium, all of the promethium that's there is eventually going to decay into samarium. So the samarium concentration with time will will vary and will actually end up increasing because you've got some amount of samarium that was there at the beginning. You've got this initial amount of promethium that's going to continue to decay into samarium, and samarium is stable. So samarium can only be lost if there's a flux that can make it absorb neutrons. But if the samarium has no flux to make it be absorbed, then the concentration of samarium can only be built up. It can't go away until we then turn the reactor back on, turn our flux back on, and let that samarium start absorbing things so that it can start going away. So if we want to think about after the shutdown and we let time go forward, what concentrations do these nuclei build up to? We would take these new equations for the post-shutdown solutions, and we would evaluate them as t goes to infinity. So that's what we're going to do here. We're going to take these post-shutdown equations, and we're just gonna make a note that the only way that samarium could be lost is by neutron absorption. And we can't have neutron absorption if we shut the reactor down. So what we're going to do is we're going to take the limit as t goes to infinity of these two equations, and what we're going to see is that if I let t go to infinity, then this exponential right here for the promethium is going to go to zero, right? So that means that the final concentration of promethium is going to go to zero. Whereas for the samarium equation, again, if I take the limit as t goes to infinity, this exponential term is going to go to zero. So I'll have 1 times this promethium equilibrium concentration plus the equilibrium amount of samarium. So that's what's going to happen with the samarium. It's going to look like the equilibrium amount of samarium that I had before I shut down, plus the equilibrium amount of promethium before I shut down. All of that promethium is going to decay into samarium, and then my samarium concentration is going to continue to grow. So, in terms of what we said about the samarium, this is a picture that kind of neatly shows what our samarium would be doing. Time zero is when we started the reactor with fresh fuel. As we turn the reactor on, we build up an equilibrium amount of samarium. That's during the startup phase with a constant flux. And then we're saying going from here to here, we've shut the reactor down. So the flux in the reactor goes to zero, and that is the point when all of the promethium in our reactor decays into samarium. So this initial amount of samarium that we had, the overall concentration of samarium increases by how much promethium was there to decay into samarium. And because the samarium only goes away when it absorbs neutrons, the only way we can get this samarium to start going back down is by turning the reactor back on. And once we turn the reactor back on, immediately what would happen is that the samarium would start absorbing neutrons, so the samarium concentration would begin to dip. And it would actually end up dipping below the equilibrium concentration it reached before. And the concentration of samarium takes a while to start building up because to start building up samarium, there's a decay chain that has to happen. I have to first build up promethium, which then has to have like 50 hours to decay into more samarium. So if I turn the reactor back on after a shutdown, then I'll see my samarium go down. I'll see it start to go up once promethium builds up and then starts decaying. And then eventually, if I turn it back onto the same flux that I was at before, it'll come to the same equilibrium concentration that it had at the beginning of when I turn the reactor on for the first time. So this graph kind of neatly illustrates what we've been talking about. You should be able to use the equations that we've been given and these taking those limits to understand how this picture comes about. You should be able to explain the different parts of this picture, and you should be able to know the features of it. I could certainly ask you to like sketch something like this on the final exam, for example. Um, And so, yeah, the only thing that we want to kind of mention here is that the only way we can build up samarium, the only way for that built up samarium to be removed is by burning it or by absorbing a neutron. Okay. So this is showing how the value of our flux will impact how much samarium gets built up. Um, this has to do with the fact that the buildup of samarium is dictated by the buildup of promethium. And if promethium is produced from fission, then if we have a higher flux, we're going to get more fissions. That means we're going to get more promethium. And that means that at that higher flux, we have more promethium that can become samarium. So this is showing effectively the concentration of samarium as as a function of the neutron flux. And as the flux increases, you build up more samarium because it comes from the promethium, which is flux dependent. Um, and this is kind of showing what we were seeing on the previous slide, where you've been running for a really long time. So you've got an equilibrium concentration of samarium. You're shutting the reactor down. And so once you shut the reactor down, samarium has no way to be lost. And it can be gained as all of that promethium eventually decays into samarium. So that's why this concentration of samarium goes up. And then I'm starting the reactor back up at this point. Once I start the reactor up, flux is turned back on, neutrons can be absorbed into the samarium, which makes the samarium go away. So this little picture right here is just this part of the picture that we are seeing on this slide. So that's everything we need to know about samarium. And then the other guy that we want to be familiar with is xenon. Um, in terms of absorbing fission products, xenon is the most important because it has the highest thermal absorption cross-section. The absorption cross-section for xenon at thermal energies, so around like 0.025 eV, is about 2.7 times 10 to the 6 barns. So we'll say sigma A for 135 xenon is approximately 2.7 times 10 to the 6 barns. So that's like one of the largest cross sections that you can find is the absorption cross section for xenon. Its absorption cross section is so large that, as you can see on this plot where the orange line is the xenon absorption cross section, it basically dwarfs all of the other cross sections that we have in our reactor. So once you start building up xenon 135, it's going to readily start absorbing neutrons, and it's going to be such a big absorption cross section that it could actually affect the overall absorption characteristics of our reactor. So we need to know where xenon comes from, and we need to know how xenon might be lost. Xenon actually comes directly from fission. So you can have fission reactions that directly produce xenon 135, and you could have a certain yield of fissions caused by neutrons of group G that make a fissionable nuclide of type I produce xenon 135. So one of the gain, here's our xenon right here. One of our gain mechanisms for xenon is from fission. You can also get xenon because of decaying of another fission product. So tellurium 135 is another fission product that is radioactive and will go through a series of decays that will produce xenon 135. So if we think about xenon, its gain mechanisms, it's produced directly from fission and it's produced from the decay of iodine 135. And then xenon itself, xenon 135, it is a very radioactive isotope. So once I build up xenon, it can be lost due to decay. It can beta decay into cesium 135. Xenon also being a highly absorbing nuclei, it can absorb a neutron and become xenon 136, at which point it has a much less, xenon 136 has a relatively negligible absorption cross section compared to that of xenon 135. So it could be lost due to capturing neutrons, and it could be lost due to itself undergoing decay. That's like kind of the main difference between xenon and samarium is that xenon is radioactive, so it itself can decay. If you turn a reactor on and build up some xenon, once you turn that reactor off, you could just let the reactor stay turned off, and that xenon will slowly decay away as time moves forward. Whereas with the samarium, the only way you can lose the samarium is by turning the reactor back on and burning the samarium. And it's also different in that it has multiple production pathways, where samarium just gets produced from one isotope. So this is that same fission that same like production destruction and fission product chain. And we can kind of simplify this in a couple ways. Um, Notice that the tellurium 135 has a relatively short half-life. Its half-life is only 19 seconds. So in the terms of like when we're looking at production destruction equations, which are usually over the order of like hours, that half-life is basically negligible, such that we can assume that this iodine 135 just gets produced directly from fission. We can kind of ignore the production of tellurium, and we can say that iodine 135 just gets produced as a fission from fission with a yield that corresponds to the yield of tellurium. And then we can basically say that notice that the half-life of cesium 135 is 2.3 times 10 to the 6 years. So the half-life of cesium 135 is so long that you could basically stop your decay chain at cesium 135. You don't really need to track the cesium or the barium because that half-life is so long. So if I make those assumptions, then I can write conservation or production destruction equations for iodine and for xenon. And those are the only two things that I have to keep track of. And these are production destruction equations, so they're going to look like a conservation statement. It's going to say change rate equals gain rate minus loss rate. So if we do it for iodine 135, we're going to say the change in the amount of iodine, I'll just say I dt. That change rate is equal to all the ways I can gain iodine minus all the ways I can lose iodine. And iodine, we're saying iodine is getting produced directly from fission. So there's a fission yield. And then iodine 135 itself is radioactive. So it gets gained from fission and it gets lost by decay. So we have a minus and then we have a decay loss. So that's like kind of just in terms of words, what our conservation statement's going to look like. And then we can write these mathematically by recognizing that the fission yield is just my fission rate density times this yield of tellurium. So it's going to look like sigma F times the flux. That's my fission rate density. And then I multiplied that by the yield of tellurium. And that says of all of the fissions per unit volume and per unit time that happen, this multiplier tells me the fraction of those fissions that end up producing iodine 135. So that's my production term for iodine. And then it's lost because of its self-decaying. And a decay loss is going to look like a lambda, a decay constant, times a number density. So this is going to look like the decay constant for iodine times the number density for iodine. And so that is what my conservation statement looks like for iodine. Gains from fission, losses from decay. And we can do something very similar for xenon. It's just that there's going to be more terms because xenon gets produced in multiple ways and it gets lost in multiple ways. So we can say the change in the amount of xenon with respect to time is equal to And it gets produced in two ways. It gets produced directly as a fission product, so we can say it has a gain term due to a fission yield. It also gets gained because of the decay of iodine 135. So it has a fission yield and a decay gain. And then it has two loss mechanisms as well. Xenon itself is radioactive, so it can decay, which means that it also has a decay loss. And xenon can capture a neutron. If it captures a neutron, it would become something else. So it has a loss due to a capture. We can say minus a capture loss. So that's what my statement would look like in terms of words. And then we can fill out equations for each of these terms. If I think about my fission yield, again, it's going to look like a fission rate density, but then times the yield for xenon. So it's going to look like a sigma F times a flux, and then times the yield for xenon. That's my fission yield term for xenon. The iodine decays and produces xenon. So the decay loss for iodine is also the decay gain for xenon. The gain term for xenon looks like a plus lambda for iodine times the number density for iodine. Xenon gets lost from decay as well. So the decay loss is going to look like the decay loss for xenon. So there's going to be a decay loss that looks like lambda for xenon times the number density for xenon. That would be my decay loss. And then the capture loss is going to look like basically a capture rate density. So it's going to look like a number density times a micro cross section for xenon times a flux. So I can say minus a flux times the number density of xenon times the absorption cross section for xenon. So that is in terms of the mathematics what this differential equation for xenon would look like. Fission gain, decay loss, and capture loss. Hopefully that makes sense. That's just kind of using definitions that we've been talking about throughout most of the class, but just in the context of this decay chain. If that's okay, then we can move forward. Um, so if you kind of compare these two equations, what you want to just be able to recognize is that um, iodine is lost because of iodine decaying, but also the decay of iodine becomes a production term in the xenon equation. So um, what we're going to end up seeing is that because xenon is produced from iodine decaying, then the amount of xenon that I have is going to depend on how much iodine that I have. The amount is going to depend on the atom density of iodine 135 at the time t. How much xenon I have at some time t is going to depend on how much iodine I have at that time. And then xenon itself gets produced from fission. So that means that the production of xenon depends on the flux, and it gets lost because of absorption. So that means that the amount of xenon there, its production and its loss, both depend on the flux. So it's going to depend on the flux and the react. And we can call that phi. And we can assume that it's constant. We can treat the flux as being constant in these problems. So what we're after are the beginning of life equations that basically say, if I start my reactor with fresh fuel, how does my xenon build up in my reactor? So if the startup time is at T0, which is 0, then I can assume that my initial concentrations of the xenon and the iodine are initially zero. So I can say that the amount of xenon at T0 is equal to zero. And I can say that the amount of iodine at time T0 is also equal to zero. If the reactor hasn't been turned on yet, then I haven't built up any fission products. Therefore, I haven't built up any xenon or any iodine. So these would be my initial conditions that are used for the differential equations that we had built up. And if I solve those ODEs on the previous slide with these initial conditions, then these are the solutions that I would come up with. And again, you would have to use integrating factors to find these solutions. So that's not really something that I would ask you to demonstrate on an exam. But that is where these equations come from. It's not magic, it's just integrating factors. And the xenon solution looks a lot more complicated because of what we were saying here, that the amount of xenon depends on the amount of iodine. So I would first have to solve for this iodine equation. I would have to plug that iodine equation into my xenon equation, and then I would have to carry out the integrating factors with that more complicated expression for the iodine as a function of time. But nevertheless, these equations tell me once I start the reactor up, how did the concentrations of these nuclei form as the reactor operates. And so we might be curious to say, if the reactor's been operating for like a couple hundred hours, how much of these isotopes have been built up? In other words, what are the equilibrium concentrations of these nuclei? And again, to find them, we're going to just take the limit as t goes to infinity. Take the limit as t goes to infinity. And so we can say that the amount of iodine at infinity, in other words, this would be our equilibrium concentration of iodine, is going to be what I get with this iodine equation when I let t go to infinity. And if t, the only place I see t is in this exponential, and it's a negative exponential. So it's kind of like the same story that we were seeing before, where if I take the limit, this exponential goes away. And so the only thing that, my equilibrium concentration of iodine is just going to look like this multiplier that I have up front. So it's going to look like the flux times the fission cross-section times the yield for tellurium divided by the decay constant for iodine. That would be the equilibrium amount of iodine that I get in my reactor. And so notice that the amount of iodine depends on the flux, that this is a flux-dependent quantity. If I operate my reactor to higher flux, I'm going to end up building up more iodine because the iodine comes directly out of fission. And then we can say something similar. We can write the equilibrium concentration of xenon would look like this. And if I were to do the same thing and take limits as t goes to infinity, then notice both of these exponential terms right here would go to zero. So this entire second term is going to drop out of my equation. This exponential is also going to go to zero. So therefore, the only thing that gets left is this first multiplier in front of xenon. So it's going to look like phi times that. That's a bad sigma. It looks crazy. Phi times my fission cross-section times the yield of tellurium plus the yield of xenon. And then that's all divided by the quantity, the decay constant for xenon plus the flux times the absorption cross-section, the microscopic absorption cross-section of xenon. So that would be how much xenon gets produced. And notice that the production, that the equilibrium of xenon also depends on the flux. So this is also flux dependent. And it's just important to note that this is one way to find the equilibrium concentrations. You could start with these more complicated expressions. If you knew what these expressions are, you could take the limit as t goes to infinity to find these equilibrium concentrations. But I can, if I'm at an equilibrium, it means that I'm at the point where the amount of my xenon and the amount of my iodine is no longer changing. So in other words, this happens when my original equations have time derivatives that are set equal to zero. So I could find this result in maybe an easier way, which would be to just setting the derivatives in the original equations to zero. I can do this by setting the derivatives in the ODEs equal to zero. And so if you kind of look at the differential equations that we wrote and look at these forms of the equilibrium concentrations, hopefully you could see that if we were to set those derivatives equal to zero and then solve for the corresponding number densities, that this is the you would get the same thing. Um, so if you think about the iodine solution and the xenon solution, if you look at these exponentials, we kind of have two different time constants that are involved, where if I think about like back to the point kinetics equations, where we had e to the omega t, that omega was what we called the time constant. So if I look at the iodine solution, my time constant looks like a lambda 1. So the time constants look like a lambda I. It either looks like a lambda I or it looks like this thing right here. It looks like a decay constant for xenon plus a flux times an absorption cross section for xenon. So if these are my time constants, then we could talk about the time that it takes for the amount of these things to drop by a factor of e, which would just be the reciprocal of these time constants. So if I do 1 over lambda I, and I use typical values for the decay constant of iodine, then I'm going to get approximately 0.1 hours. So it takes about a tenth of an hour for the amount of my iodine to change by a factor of E. And if I look at the other time constant, the 1 over the lambda for xenon plus the phi times the sigma A for xenon, if I use typical values for that, I get about 30 hours. So that means that if you have that number, then it can tell you that even if you have a small flux, it's going to take about 30 hours for your xenon to build up an equilibrium amount. So that's like a good kind of number to just keep in mind, that it's like over the first 30 hours of a reactor being turned on is when my xenon concentrations are going to be being built up the most. And after 30 hours, we're going to kind of hit an equilibrium amount of xenon. And it's kind of like a similar story with promethium in that xenon is very highly absorbing. So over the first 30 hours, I've built up all of this xenon that has this massive absorption cross section, and the equilibrium amount is going to stay in there until I do something different with my reactor. So after 30 hours, I've like kind of maxed out the xenon that's there. And if I don't know about that, then I'm going to turn my reactor on. It's going to be critical. It's going to run for about 30 hours. But then even before those 30 hours are up, my reactor is probably going to go subcritical if I don't know about the xenon and I don't have some way to counteract all of the negative reactivity that that xenon buildup is going to cause to my system. So that's how they build up after a startup. And then once we've built them up, at some point we're going to have to shut the reactor down. So we want to ask the question, how do these nuclei concentrations evolve after I then decide to shut the reactor down? So I'm going to assume that we're operating at a constant flux of phi zero before we shut it down. And then at the time t0, a new time t0, we're going to shut the reactor down, which brings the flux down to zero. So at this new T0, these are my equilibrium amounts of xenon and of iodine and xenon. And these were what my differential equations looked like when the reactor was operating and when there was a flux. But if I've now shut the reactor down, these differential equations are going to simplify because now the flux is zero. So this iodine concentration equation, basically what we're saying is that any term that has a flux is going to go to zero once we've shut the reactor down. So therefore, my iodine concentration is just going to look like the decay constant of iodine times the number density of iodine. because the flux goes to 0, so that term drops off. And then for xenon, it's going to look like a positive lambda I n I minus a decay constant for xenon times a number density for xenon. So I'm going to have a lambda for xenon and a number density for xenon. These are what my differential equations now look like once I've shut the reactor down. These would be like my post. These are like my post shutdown equations. And these are like my initial conditions, because this is the amount that I have of those nuclei at the moment that I've shut down. So these are like my post shutdown initial conditions. So if I say at time t naught, I've shut the reactor down, and I were to use these as my differential equation, these are my initial conditions for those differential equations, and I were to solve them subject to these initial conditions at t0, then I would end up getting that the iodine equation is going to look like a decaying exponential, which is hopefully what we would expect from a differential equation like this. The iodine is just going to exponentially decay. Whereas for xenon, it's going to look a little bit different because the xenon gets produced from iodine and it gets lost from itself decaying away. So the number density for iodine is just a decaying exponential. The number density for xenon is more complicated because it gets gained from iodine decaying and it gets lost from it itself decaying. So what we would then want to say is once we've shut it down at T0, how much longer after T0 does it take for my concentrations to come to a new equilibrium? And what would those new equilibrium concentrations look like? So we're going to take these post-shutdown solutions and we're going to evaluate them as T goes to infinity. So if we do that, again, we're taking the limit as T goes to infinity for both of these guys. And we're going to be able to see that the amount of iodine, uh, the amount of iodine, my iodine function is going to approach a certain value. And we're going to see that the xenon function is going to approach a certain value. And if I look at my equations carefully, what I would see is that every term contains an exponential that's negative. And so all of these negative exponentials are going to go to 0. That means that the amount of both of these nuclei is going to go to 0 as as time goes forward after the shutdown. So eventually I'll have no iodine in the reactor, and eventually I'll have no xenon in the reactor. Both of them will eventually go to 0, but they're not going to go to 0 in the same way because iodine only decays. Iodine only has a negative exponential, whereas xenon can first get produced before it eventually fully decays away. And that's because of the differential equations. That iodine just continuously decays because it has no gain term, whereas xenon can gain from the iodine disappearing, and it also itself gets lost because of its own decay. So xenon can be built up a little bit before it eventually decays to 0. So the main thing that we would want to know is like, how does that concentration change for xenon as after I've shut down, and how does the flux have to compare to the other parameters in my equations such that I can be able to understand when does the amount of xenon increase or when does it decrease? So these were the equilibrium concentrations that we had before we shut down. And what we want to do is think about if we were to take our xenon differential equation and then the post-shutdown differential equation and just evaluate it at that initial time. So if I were to take my xenon concentration and evaluate it at that initial time, then this is just the left side is just saying this is how my xenon is changing at that shutdown moment. And on the right-hand side, I'm basically just evaluating these guys at T0, and at T0, they had their equilibrium amounts. So this is going to look like the lambda for iodine times the amount of iodine in equilibrium. And this is going to look like the decay constant of xenon times the amount of xenon also at equilibrium. I'm just evaluating these at T0, and at T0, these concentrations were those equilibrium values. And then we can sub in these definitions for the equilibrium amount of iodine and the equilibrium amount of xenon. So then this is going to look like lambda for iodine times phi 0 times sigma f times the yield of tellurium divided by the decay constant for iodine. So those iodine decay constants are going to cancel each other out. And then on the second term, I'm going to have the decay constant for xenon times the equilibrium amount of xenon, which is this guy right here. So it's going to look like phi 0 times my fission cross section times the yield of tellurium plus the yield of xenon divided by the decay constant of xenon plus that phi 0 times the absorption micro cross section for xenon. So ultimately, what we're concerned with being able to figure out is how does this phi 0 have to compare? Like, what does it have to be larger or smaller than such that we can be able to say if the amount of my xenon is increasing at that shutdown point or if the amount is decreasing at that shutdown point. If this thing is positive, then it means my amount of xenon is increasing after the shutdown. And if this thing is negative, then it means my xenon is going to decrease once I've shut the reactor down. And it's going to depend on the flux. What you're basically going to do is you're going to kind of take these equations and you are going to kind of get like a, well, you're basically going to do some algebra. Um, you're going to do some algebra and be able to get this into a form that looks like sigma f times the yield of tellurium. And then you're going to have this big fraction. In the numerator, you're going to have phi 0 minus the quantity. I'm just it's gonna be tight here. So I've got the yield of xenon, and I've got the decay constant for xenon. Then I'm dividing by the yield of tellurium times the absorption cross-section for xenon. That's what I'm going to have in the numerator. And then in the denominator, I'm going to have 1 plus the decay constant for xenon divided by the phi 0 times the sigma A for xenon. So what I'm trying to say is that you can take this expression, you can do algebra on this right-hand side to get it into this form, and you want to get it into this form because then what we can recognize is that this term up front, the cross-section times the yield, that's always going to be positive. This denominator is 1 plus quantities that are always positive. So the denominator is also always going to be positive. So therefore, the sign, the SIGN of this derivative is going to just be based on how does phi 0 compare to this term. If phi 0 is bigger than this term, then I'm going to have a positive on the right-hand side, and therefore my derivative will be positive. And if the phi 0 is less than this term, then I'm going to have a negative sign here, and therefore I'm going to have a negative for the derivative. So my phi 0 has to be greater than this term right here. It has to be greater than the yield of xenon times the decay constant for xenon divided by the yield for tellurium times the absorption cross-section for xenon. If my phi 0 is bigger than this term, then that means my derivative will be positive, and therefore it'll mean that after I shut down, the amount of xenon will actually increase before it eventually decays away. And if the phi 0 was less than this, then once I shut down, the amount of xenon would just end up exponentially decaying away. So the amount of xenon in our reactor is flux dependent, and that's what this slide kind of helps us to see, that how much xenon builds up depends on the level of the flux in the reactor. As the flux gets higher, I build up more and more and more xenon. And xenon is so highly is such a good absorber that you can get to a point where the absorption of your xenon kind of overpowers all of the possible like excess reactivity that you could dump into your system. Like this maximum reserve reactivity is basically saying how much reactivity could I add to my system if I just removed all of my control rods? And the amount of negative reactivity from the xenon can overpower that maximum reserve reactivity such that it would be really dangerous if I tried to operate the reactor during this period where my radioactivity or the negative reactivity of the xenon was so high, because I could get to a point where I removed all of my control rods. I could think that by removing all of my control rods, I would be like trying to shut the reactor down, but really the reason that the reactor would be shut down still could be that I have just so much xenon in the reactor that that shutdown kind of like becomes, or that really that the reactor would stay shut down until the point where I've burned up all of that xenon or all of that xenon has decayed away. And then I would very quickly go from a situation where that xenon is now gone and I've removed all of the control rods from my reactor. And then you're going to very quickly go from subcritical to supercritical. And that's part of what happened with Chernobyl. They were doing tests where they were trying to get the reactor to a certain power level. They didn't realize that in the process of getting there, they had lowered the power a lot. In lowering the power, they had built up a bunch of xenon. They didn't leave it shut down for long enough. They removed all of the control rods from the reactor, and they got their reactor in a very dangerous configuration that resulted largely from them not really understanding how the buildup of xenon was going to impact the reactor operation. Um, so Yeah. Um, the this is a phenomena because of xenon being flux dependent. The amount of xenon in your reactor can increase by like a factor of two or more before you actually run out of the iodine that produces the xenon. Um, and this is more prominent at higher fluxes because higher fluxes mean you get more production of your xenon. Yeah. This dead time is basically telling you about how long you would need to wait before it would be safe to restart your reactor to avoid these concerns about the xenon. And so this plot is kind of showing just an illustration of what we've been talking about the xenon. That you start the reactor up, post startup, the concentration of xenon gets to an equilibrium. And then depending on the flux, this is assuming that the flux is high enough that the amount of xenon would continue to increase after the shutdown. So I've shut the reactor down, but the amount of xenon continues to build up because the iodine that was in my reactor is producing more xenon. Um, and I've also taken away the flux. So I've taken away one of my loss mechanisms for xenon. Um, and so, but naturally, xenon is radioactive, so it would like the concentration would increase, it would reach a maximum, and then it would begin to decrease as that xenon starts to decay. And then at this point, I could restart the reactor. And depending on how, I guess there's two plots that are shown. One of them, the black one, is showing restarting at a new flux. The gray one is showing the xenon, what happens to the xenon if I were to just keep the reactor shut down and not restart it. So if I don't restart it, then that amount of xenon just continues to exponentially decay away. Whereas if I restart it, then the moment that I restart, I've turned the flux back on. That means that the xenon will start to absorb neutrons. So it'll actually have two loss mechanisms. It'll be lost because of its decay, and it'll be lost because of its absorption. So in the restart case, it actually drops faster, but then it eventually picks it back up because after a certain amount of time, my fissions have produced more iodine. My fissions have also started to produce more xenon, and the production of xenon means that I get to a minimum, but then eventually get back to the same equilibrium that I had before if I turn it back on to the same flux level. So the reason that my concentration drops faster upon this restart is because the xenon has two loss mechanisms. The xenon will experience two things. It experiences absorption loss and it experiences decay loss. And it doesn't really start producing until I've started to build up iodine. So production, that would kind of like be the third point, is that production is minimum. You could say the production is small until I form iodine, until 135 iodine is formed. So Xenon is a little bit more complicated because it has multiple gains and multiple losses, but fundamentally we care about it for the same reason that we care about Samarium. It's very highly absorbing, which impacts how we have to operate our reactors if we want to do so safely. So this is just kind of really just rephrasing things that I've already been talking about. Um, Xenon is very highly absorbing, therefore its production results in a increase of negative reactivity to the system. Um, if you have some equilibrium amount of xenon in your reactor, then you have to be able to account for that. Like as that xenon builds up, you're probably going to remove your control rods a little bit so that the negative reactivity of your xenon can be counteracted with a positive reactivity insertion from removing control rods. Um, Pressurized water reactors also have boron in their coolant, which is another absorber that can be online, can be adjusted online such that you can lower your boron concentration as the reactor operates. And that decreasing of the boron concentration can allow for more excess reactivity that could be balanced with the reactivity of these fission products that are getting formed. And yeah, this is showing that same plot where we kind of have a shutdown period. So we were in equilibrium, we've shut the reactor down. And once we've shut the reactor down, the amount of xenon builds up, gets to a maximum, and then it starts to finally decrease once that xenon is allowed to decay away, and once all of the iodine that was there has decayed into xenon. So the iodine is decaying and producing more xenon. Eventually, there's no more iodine left, and then the amount of xenon just exponentially decreases. And then once I start the reactor back up, there's a period where my my xenon concentration decreases even faster because it's being lost due to absorbing neutrons and it's being lost due to its own decay. Um, this is showing how your xenon and your iodine concentrations would vary as you change the flux in your reactor, starting at some initial flux V0, decreasing it to a new flux V1, and then raising it back up to the same flux V0. So what happens with the iodine is that it's got some equilibrium concentration that's been formed at this constant flux, and then I decrease the flux. If I decrease the flux, that means that the iodine production goes down because the amount of iodine is produced is proportional to the neutron flux. So I lower the flux. That means that I lower the iodine concentration, and it would get lowered to a new equilibrium. And then once I turn the reactor back on, my flux is, or I turn the reactor back to a higher flux. That flux allows for more fissions, which allows for more production of iodine. So that iodine concentration would slowly build up until it got right back to that equilibrium value consistent with whatever this V0 value is. Whereas xenon, it was also at equilibrium before I changed the flux, but the decreasing of the flux results in all of this iodine. As it's decreasing, the iodine is decaying away and it's producing more xenon. So the amount of xenon actually goes up until all of that iodine is like at a new concentration. Really, as the iodine is getting to a new concentration, my xenon is also decaying and getting to its own new concentration. Um, and then once I turn the reactor back on, the iodine concentration, sorry, the xenon concentration dips even quicker because it's decaying and it's getting absorbed. It's absorbing these neutrons at the new flux level. Oops. So it, oops, sorry. So it would decrease quickly before building back up to a new equilibrium once I ran the reactor at that at the original flux for a certain amount of time. Um, so that's what we want to be able to kind of say about xenon, about samarium, and about understanding how they evolve in our reactor when you turn the reactor on to when you run that reactor for a long time, and then when you shut the reactor down, and then when you maybe turn the reactor back on after you've shut it down. Um, and this last slide is just talking about something that can happen called xenon oscillations. This is a consequence of the fact that the buildup and depletion of your fission products depends on the flux in your reactor. And so if you imagine your reactor to be like a bunch of reactor assemblies, and you imagine that your reactor is operating at constant power level, and maybe in one location in your reactor, you remove a control rod, and in another location in your reactor, you insert a control rod by the same amount, such that the overall reactivity is the same. But now you've got one place where the reactivity is, well, where you've removed the control rod, your reactivity would go up. So that would be like your increased flux region. And where you've inserted the control rod, that would be where your reactivity has gone down. So that would be your decreased flux region. In the place where you have a higher flux, the xenon gets more quickly burned away because of the higher flux. That xenon going away results in a reactivity addition because of the fact that that xenon is no longer, not as much of it is there to absorb things. That increase in reactivity causes a further increase in flux, which increases the amount of xenon that gets burned up. And so in this location, you basically have like positive feedback effects from what's happening with the xenon going away. Whereas in the decreased flux region, it's almost the opposite, that you have a lower flux, so the xenon can increase because it's not being absorbed as fast. That causes reactivity to decrease. Because that results in reactivity decreasing. The decrease in reactivity decreases the flux. That lower flux causes more xenon to be formed because you're continuing to produce the xenon from the decay of iodine, but you're not as efficiently burning the xenon up because your flux is lower. And so you have one place where and you have these two locations where your concentrations of iodine are varying. And so this is something that can happen in reactors. Eventually, you will have these kind of oscillations dampen out because of things like feedback. You could also account for it from the reactor operator side by like adjusting control rods in the you could compensate for this by adjusting control rods in a certain way. But yeah, these oscillations can last over like 15 to 30 hours. If you have these oscillations occurring, it is kind of bad for reactor operation and it can affect your component integrity. If you have one place where you have like a high flux and one place where you have a low flux, that means that in one place you're going to have a higher power, you're going to have a higher burn up, and one place you're going to have a lower power and a lower burn up. Higher power would mean higher temperatures in one case and lower temperatures in another case. So you got to be able to monitor these things. Real reactors would be monitoring these things and adjusting accordingly, such that if it did occur, they would take actions to try to mitigate the xenon oscillations. And I think that's everything that I wanted to say about chapter 8. So that's going to conclude production destruction equations and fission product buildup. The next lecture will be the last lecture with new content. That'll be on Wednesday. That'll be the video that I post for y'all. And so, yeah, at this point, I can pass back your exams, but also if y'all had any questions about anything relating to this lecture or anything else, feel free to let me know.